Um, Welcome to today's session. Okay, so
Good morning, sir. Good afternoon.
this is session number 10 in basic calculus for us. We are gradually coming towards the end of this section of basic calculus. So towards the end of the last lecture, we had looked into the basics of indefinite integration. So let's start with a recap of that concept. Okay, so we saw that indefinite integration is a process by which it is an operation to calculate what is called the antiderivative of a function. So basically, if the derivative of a certain function ix is fx, then we say that ix is the antiderivative. That is the opposite of derivative of fx. Okay. So integration of fx will result in antiderivative. So basically, just like differentiation of a function gives its derivative, like that integration of a function gives the antiderivative. So for example, we know that differentiation of x square plus any constant is equal to 2x. Okay. So that means integration of 2x should be equal to x square plus any constant. So we say that this is the antiderivative of the term 2x. So this was the meaning of the operation of indefinite integration. The purpose of indefinite integration is to find this thing called antiderivative, where antiderivative is defined by this relation. That if the derivative of a function is fx, then we say that that function is the antiderivative of fx. Okay, so to that extent, what we had seen is that we know that differentiation, for example, we know that differentiation of any linear term is a constant. So k is a constant over here. So that means integration of this should be equal to a linear function. So for example, integration of 5 is 5x plus c, where c is any real number. So c is called the constant of integration. And it is what we call an indefinite constant because it does not have a definite value. So it can take any real value. So like that integration of, let's say, minus 20 is minus 20x plus c. So we can just see the proof of this, that if you differentiate this, you will get minus 20. So that is clearly showing us that minus 20x plus c is the antiderivative of minus 20. So this was like the first property that we had seen, that, or rather not this, but this one, that integration of a constant or antiderivative of a constant is a linear function. Antiderivative for a constant, say k, is a linear function, kx plus. Okay. Now likewise, we can see that differentiation of x square is equal to 2x. So that means integration of 2x is x square plus c, or we can see that differentiation of x squared divided by 2 plus any constant will give us x. So that means integration of x dx is x squared by 2 plus any constant. Okay. Now likewise, differentiation of x cube is 3x squared. Okay, so that means integration of 3x squared should be equal to x cube plus any constant. Or if we divide x cube by 3, then its differentiation will just give us x square. So that means integration of x square is x cube by 3 plus c. Okay, so we're getting like a series of terms like this now. You can see integration of x to the power 1 is x to the power 2 by 2. Integration of x to the power 2 is equal to x to the power 3 by 3. So like that we get a trend and we get a general formula for integration of x to the power n. Okay. Yeah, so Yash, hope this answers your question that antiderivative of a constant is a linear term. Like if that constant is 5, then antiderivative is 5x plus c. Is it clear, Yash? Right, so antiderivative for a constant is a linear function. But like that, antiderivative of x is x square by 2 plus c. Antiderivative of x square is x cube by 3 plus c. We get a series of terms like that. Okay. Okay. So now finally we see that if we take the series forward, we get the equation that x to the power n, its integration becomes x to the power n plus 1 upon n plus 1 plus c. So this now becomes our general formula, but albeit here n can take any real value other than minus 1. N should not be equal to minus 1. Okay. So this is the general formula for powers of x
So,
other than x power being minus 1.
so
Yes.
what would happen if we take -1?
Yeah. So for that we had seen the exception. It was ln x. We know that differentiation of ln x, natural log of x, is 1 by x. So
Yes.
integration of 1 by x. This is the case of x to the power n, where n is equal to minus 1. In that case, is equal to natural log of x plus c. So this one is the exception to this rule. Okay, this is the exception case.
So,
Yes.
what if we put the value of -1 in the formula which you have written in the red box?
It gives you an indeterminate term, no? Because
Yes, sir.
denominator becomes 0, so it's undefined.
Undefined. So, sir, it should come undefined. Why?
No,
ln x?
it should not come undefined, and that's the whole point. So that's why we cannot define as n equal to minus 1 in that formula. That formula is applicable only for all values of n other than minus 1. And there is that exception which is related to that formula. Okay, so this formula is applicable for all values other than n equal to minus 1. For n equal to minus 1, it's this formula. The exception case, it is this formula. Again, is it clear?
Yes, sir, clear.
Sir,
Yes.
sir, actually it is ln of mod x, right?
See, the thing is, yes. I mean, it becomes this way actually. It's not exactly ln of mod x. I'll explain. Just a moment. File has crashed. Yeah, so in case we have a negative term, we have to treat that negative sign as a constant of -1. Okay. You're understanding the point? So suppose we are integrating -1 by x dx. So here what we do is we use the property of integration, that is integration of a constant into a function is equal to constant times integration of the function. So we use this property here and take the -1 outside. Okay. So it becomes minus of ln x plus c. So that is the same thing as ln of x to the power -1 plus c, using the property of.
Okay, sir.
Understanding the point? Okay.
Sir, won't it be negative c?
Which one negative sign?
Sir, because we have taken minus outside, no?
Yeah. So it is minus of ln x, no?
So, sir,
Integration of dx by x is ln x. So it becomes minus of ln x.
no, sir. Similarly, it is like integration of 1 by x is ln x plus c, and we have a minus outside the bracket, right?
Yeah. So the minus power sign, when it comes inside, it becomes a power because of the property of log. No? A times log b is log of b to the power a. Got it? No?
Okay, sir.
Okay. So for example, minus of ln 5 is the same thing as ln of 1 by 5 or 0.2. Okay. But
Okay.
ln of a negative number cannot be defined. Okay. Ln of a negative number, this is undefined. Because basically when we say ln x is equal to y, it means that x is equal to e raised power y. No? Now whatever value of y we take, x cannot be a negative quantity. No? So we cannot define ln of a negative number.
Yes, sir.
So the natural domain of ln function is only positive numbers, x greater than 0. Okay, anyhow, so we won't worry too much about that. So coming back to the basic formula of integration. So we saw that the fundamental formula that we have is this, but with the exception that n should not be -1 for all n except n equal to -1. So the exception case for n equal to -1 becomes, so this is the exception to the above formula. Then we have the properties. So these two formulate. Okay, then we have properties. So the first property we have just seen actually earlier today, that integration of a constant is a linear function. Then the next one was integration of a constant times a function becomes constant times integration of the function. So for example, if I have integration of 2x cubed, I'll take the 2 outside and then I will apply the formula. So this will become 2 into x to the power n plus 1 upon n plus 1. So that's 4 in this case plus c. So we can see that antiderivative of this function 2x cubed will finally come out to be x to the power 4 by 2 plus c. Now the simple way to understand why this is correct is that you can always check that if you differentiate this, x to the power 4 plus 2 plus c is the antiderivative of which term? Of 2x cubed. So that means if I differentiate this, I should get this. And you can see that that's happening. So that means this is the correct evaluation of it. Okay. So that is this second property. And the third and final property is that integration of the sum of two functions or the difference of two functions, we can use the distributive kind of property. Integration of this first function plus or minus integration of the second function. So using this, you can see that all simple algebraic functions, including polynomials, etc., we can easily integrate by using this. So an example of this would be, you want to do integration of root x plus x root x. We'll just break this into two integrals. Integral x to the power half plus integral x to the power 3 by 2. And then we'll just apply this x to the power n rule here to both of these. So this one will become x to the power 3 by 2 divided by 3 by 2. This one will become x to the power 5 by 2 divided by 5 by 2. And we can combine the constant of integration and write as 1c. So this is 2 by 3 x to the power 3 by 2 plus 2 by 5 x to the power 5 by 2 plus c. Or we can simplify it a little more and write it like this if we like. So that's just a matter of preference how we write it, whether we write it like this or like this, both are correct. And you can always check that this is the correct antiderivative by doing this. You can check that when you differentiate this, you should get the original function which we had integrated. So that will immediately tell you whether your answer is correct or not. Okay, so hope these two examples are clear to all of you, apart from the properties and the formulae. We'll discuss more properties and formulae today. Right, so going ahead. Okay, Ansh and Yash, I will just scroll up. We have to go through the earlier section once. This part or the earlier part?
Yes, yes.
Okay, okay. Okay, so let's first do a few practice examples based on these properties. Okay, just try out these 4 questions, people. And send me your answers in the text message. I'll verify them. Okay, very good. So most of you got the answers correct. I will just verify each of them. Okay. So for the first step, what I would do is express each of them as a power of x like this, and then apply the formula properly. So this would be the final answer for the first one. This one we would need to simplify it a little bit first. So we'll express it as x plus 2 by x and then remember that this is the -1 power, so this is the exception case. So this is the answer for the second one.
So
Oh, sorry, there's a 2 outside, my mistake. Okay, now likewise, the third one, the first step would be to express this as a single power of x, bringing x to the numerator, and then apply the formula. Very good. So most of you got all these correct. Let's come to the final one. It's quite easy. So only thing is we have to first expand this in the final one. And then only we can apply the integration formula to each part.
So,
Yes.
sir, in the fourth one,
Yes.
we are doing three different integrations, matlab,
Yes.
separate. So, sir, why aren't we taking three different C's?
The thing is, like, if you individually integrate each of these, you're getting 3 constants, let's say C1, C2, and C3.
Yes, sir.
But that is equal to a constant, no? And these can take any real value. So ultimately, this constant can take any real value.
Oh, okay, sir. Got it.
So when we sum up, no, like even in the B part, we are summing up 2 integrations. We always sum up the constant and write it as a single indefinite constant, right?
Okay, sir. Got it.
Okay. No, but we cannot write that because you will see that the way you have done the integration for the D part, if you check out the differentiation of the term that you've got, you will not get the original function because it's basically a quadratic function to the power 2. So we cannot
Yes, sir. Understood.
Directly integrated that way. You understood? Na?
Yes, sir.
Okay. Yeah, I mean, there is a process of double integration, but that is not important for us right now. Shaurya, to answer your question, can we integrate twice for second derivative? It's like second antiderivative. We can do that, but it's really not that essential right now for us. Okay. Okay. Now moving on. Next thing we will see in integration is the integration of basic trigonometric functions. So integration of sin x is minus cos x, and the principle of this is very simple, that differentiation of cos x is minus sin x. So differentiation of minus cos x plus any constant is sin x. So therefore integration of sin x should be minus cos x plus c. Like that, integration of cos x is sin x plus c, because differentiation of sin x is cos x. Now after these two, the formula become a bit more complicated. Integration of tan x is given by natural log of sec x plus c, because if you differentiate natural log of sec x by chain rule, you will see you have 1 by sec x into differentiation of sec x, which is sec x into tan x. That becomes tan x. So this is, you can say in a way, this is the proof of this formula. Okay, now so these are the three primary trigonometric functions. Now the reciprocal ones are a bit more complicated. So integration of cosec x is given by the formula minus of ln cosec x plus cot x. Okay. And you can use a similar method of differentiation by chain rule to prove this. So you can do that as a review exercise yourself. And do that as a homework exercise yourself. Similarly, integration of sec x is ln of sec x plus tan x. You can do that proof also. And integration of cot x is minus ln cosec x. Anyhow, for the moment, these are going to be the more important integrations for us. These two are going to be more important in terms of application in physics. However, you should know all the 6 formulae, just like you know the formulae for differentiation. Okay. Okay, and moving on, one final formula apart from the trigonometric functions is integration of e raised power x, which is as simple as the differentiation we had seen. Differentiation of e raised power x is e raised power x. So integration of e raised power x also remains the same. So at this stage, we will not be discussing about the integration of natural log of x, which is a more lengthy process, which will come in later in advanced calculus. So these are the primary formulae that you have to remember for integration. Okay. The x to the power n rule with the exception for it, n equal to -1, the 6 trigonometric functions integrations, and the exponential functions integrations. So from a formula point of view, this is all we need for integration. Okay, so now before we move on to more advanced methods of integration like substitution, etc. Let's see a application type of question of integration. So for example, we have something like this: the speed of a particle moving along the x-axis. Yes, Darsh, you have a doubt, better?
Sir, what would be the integration of like a log of x, not natural log, but like any base log?
Yeah, so that is done by a more lengthy process, which is called integration by parts. Okay. So that we will not be studying in this basic calculus portion. We'll be studying that in the advanced calculus later in maths. Okay.
Acha. So like chain rule for differentiation. This.
No, it is actually slightly different to chain rule. It is more like an application of product rule kind of thing for
Acha.
integration. Okay.
Okay, sir.
The equivalent of chain rule is something called substitution, which we will be seeing next.
Okay, sir.
So speed of a particle moving along the x-axis is given by this relation, suppose, where t is time in seconds and v is in meters per second. Okay. So if its position x0 was equal to 2 at time t equal to 0, then find its position x as a function of time. So this you can see is the most logical type of application of integration. So let's work this question out on the board. Okay. So what we had understood earlier is that instantaneous speed is rate of change of instantaneous position, okay, or rate of change of distance. So here the particle is moving along the x-axis. So delta x is basically the distance. Okay. So speed is dx by dt. Instantaneous is like, okay. So now this, what it means is that x should be integration of dt. So it is like this, that if fx is the differentiation of ix, that means ix is what? It is the integration of fx. So like that, here it means that if v is d by dt of x, so what it means that x is integration of v. Okay. So applying that concept here, we will see that v, which is dx by dt, is given to us as 2t square plus 3t. Okay. So the derivative of x with respect to time is this. Okay. So that means the integration of this should be equal to x. Understand? So from x to v, dx by dt is equal to v. So from v to x should be this. So that is the concept we'll apply now. So x is equal to integration of 2t square plus 3t, which we can very easily carry out. So this will become so we'll write one combined constant. So we'll get x as t square by 2, sorry, t to the power 4 by 2. So plus 3 by 2 t square plus some constant. Now the thing is, the constant is an unknown term right now. So how we'll get the value of the constant? by using the other part of the statement that is given to us.
Sir,
Additionally, it is also given that x's value is something at some time now. It's given that x's value is 2 at t equal to 0. So we'll make use of this statement now.
sir, 2t cube, right?
Sorry.
The
Sorry. It's 2 by, oh, my mistake. Yes. I made a mistake in the integration. This whole thing will change. So this is 2 into integration of t square. So that is t cube by 3. So this term will become 2 by 3 t cube. So right now,
Yes, sir.
okay, plus 3 by 2 t square plus c. Now to find the value of c, yeah. So coming back to this, how we'll find the value of c? We'll find the value of c from this statement. Okay. So we'll substitute this here. So x should be equal to 2 meters at t equal to 0 seconds. Okay. So substitute this. So 2 should be equal to 2 by 3 into 0 plus 3 by 2 into 0 plus c. That means I'm getting my value of c as 2. Okay. So having got that, now I know that x is not an indefinite function. It's a definite function which has this nature. So now you can see that after substituting the value of c, the function of x that we are getting, it satisfies both the properties. That is, value at t equal to 0 is equal to 2, and also its derivative, which is the instantaneous speed dx by dt, is equal to what is given to us. That it's 2t cube, 2t square plus 3t. Okay, is this clear?
Yes, sir.
Okay, so just make a note of this quickly. Algebraic functions, power of x.
Sir,
Yes. Yes, tell me.
done.
Yeah. Okay, so hope this example is clear.
Yes.
Okay. Now you'll remember in worksheet 1, for example, we had done one type of a question, one or two, one of those, where we were given something like this, that dy by dx was ax square plus bx plus c. Okay. And it was given that y is equal to 0 at x equal to 0. Then, if I remember correctly, just a second, I'll just bring up that question. So we'll see that this type of question can now be done by integration also. Just give me a moment. Yeah, so this would have been in worksheet 2. Yeah, so y was equal to 0 at 0, then 6 at 1. Okay, so we additionally had y is equal to 6 at x equal to 1. And then we had y equal to 0 at x equal to minus 1. And again, we had dy by dx is equal to 2 at x equal to 0. Okay. So from this, we wanted to find a, b, and c. So now there we had done this question by sort of guesswork. So the approach we had taken is that if dy by dx is quadratic, okay, so that means y must be a cubic function. So we started with the assumption that y is some cubic function like this. And we had found out like this. But now you can do this by integration. Okay. Dy by dx is given to us this function. That means y is basically what? Integration of that function. So it is the antiderivative. Okay. So y is the antiderivative of this thing, ax square plus bx plus c. So you can approach this problem this way now. So try out this question, find out ABC, and like we'll see how this makes it a single step process, whereas there it was the method of solving was a little bit more, roundabout kind of method, indirect kind of method of solving. There's a more direct way of solving the same situation.
Sir,
Yes.
so we will take this c and a constant into a one indefinite c only, no?
Sorry, we will take.
Ax square plus bx ka c
Yeah, and
and
we'll
the
integrate it. No, beta?
okay.
Where A, B, C are unknown constants. There are some numbers which you don't know right now, right?
Yes, sir.
Because y is the antiderivative of this now, because derivative of y is this quantity, so that means y is the antiderivative of it, right? So to find the antiderivative, we have to integrate it, right? Okay, so yeah, very good. Let's work this out. So let's start with the step that y is integration of ax square plus bx plus c. Now let's write this constant as some c prime. So here our constant of integration is c prime. Whereas a, b, and c are those definite values. Now we have to find each of these. So for this, we will use these four conditions. Okay. So this is condition 1, this is condition 2, this is condition 3, this is condition 4. So condition 1 will tell us that y is equal to 0 for x equal to 0. So 0 should be equal to 0 plus 0 plus 0 plus c prime. So our constant of integration is 0. That is the first thing we are getting. Okay. And the second thing will tell us that y is equal to 6 for x equal to 1. So that means 6 is equal to a by 3 plus b by 2 plus c. Okay. So see this, a by 3 plus b by 2 plus c is equal to 6. And the third thing is telling us that y is 0 for x equal to 1. So for x equal to minus 1. So substitute that here, so we'll get 0 is equal to minus a by 3 plus b by 2 minus c. So minus a by 3 plus b by 2 minus c is equal to 0. So now you can see that if we just add these two equations, we get b is equal to 6. Get another term. Okay. And finally use the fourth thing that dy by dx is equal to 2 at x equal to 0. So dy by dx is equal to 2 at x equal to 0. So that means e into x square plus b into x plus c is equal to 2. So that means c is equal to 2. So now I've got c prime, b and c. Now I need to find the value of a. So from this equation we can see that a by 3 plus b by 2 plus c is equal to 6. So a by 3 plus 5 is equal to 6. That means a is equal to 3. Okay. So now we got all the values. So a is equal to 3, b is equal to 6, c is equal to 2, and c prime is 0. So that means y is equal to something gone a little wrong here, is it? No. It's a by 3, no? So this will become x cubed. Yeah. Plus b by 2 x square, so that will become 3x square plus cx, so that is 2x plus d. And dy by dx, which is the derivative of this, will become 3x square plus 6x plus 2. So you can see that all these conditions are satisfied now. So this is another example of something that can be solved using this kind of application.
So Sir,
Yes.
sir, can you just scroll up for a second? I want to see the question.
Yeah. Okay, so this is actually one of the questions from worksheet 2. This is worksheet 2, question number 5, which we had done earlier by this method. We had done it by this method earlier, but now we can do it by a more direct method.
Thank you, sir.
Oh, okay, so let's move on now. Now the next thing we'll see is a technique in integration called integration by substitution. So this is like an equivalent of chain rule for integration. Like we had chain rule for differentiation. So you can think of this like an equivalent of chain rule for integration. Now, the first part of this is when we have an integration of the type where we have to substitute a linear term. So I'll explain how that works. Substitution of a linear term. So for example, we'll actually understand this with an example and then we'll see further. Okay. So suppose we are integrating square root of 2x plus 1 dx. Okay. So you can see that 2x plus 1 is a linear term in x. So we can use this method of substitution of a linear term. So what we'll do here is that we will substitute 2x plus 1 as a dummy variable. Okay. So then what happens is that dz by dx, if I differentiate this, is equal to 2. So that means I can replace dx as dz by 2 just by cross multiplying over here. So then the integration becomes this integration of square root of 2x plus 1. In this, I can replace 2x plus 1 as z because I've done this substitution. Okay. And I can replace dx as dz by 2. Okay. So this becomes 1 by 2 integration of root z dz. Okay. Now this integration is simple enough for me because it is directly of the type single power. Okay. So now using the formula, this becomes 1 by 2 z to the power half plus 1 upon half plus 1 plus c. So this becomes 1 by 3 because half, this 2 by 3 will go into the numerator. Or let me do it in 2 steps. So we still have 1 by 2 multiplied with this will become 2 by 3 z to the power 2 by 3 plus c. And now finally we'll resubstitute z here. Okay. So these two things were substituted in the integral. Now we'll resubstitute. Next step. Okay. So after completing the resubstitution, we will see that this becomes 1 by 3. Now z was how much? It was 2x plus 1 to the power 3 by 2 plus c. So finally, our integration of square root of 2x plus 1 is given by this antiderivative. And we can always check that our answer is correct. So to check it, you should just differentiate this term.
Sir, in the second last step, it will be z raised to 3 by 2.
Just a moment. So if you do this differentiation, you can see you will have to do it by chain rule. So you will get that. You will get square root of 2x plus 1. So that means our integration is correct. Yeah. What did you say? Which step?
Sir, in the second last step.
Which one? This one?
Yes, sir. It will be z raised to 3 by 2, no?
No, it is divided by 3 by 2, no, beta? See, z to the power 3 by 2 divided by 3 by 2, no?
So then in the last step, it would be 2 by 3.
So that 2 cancels out now with this half here.
The power.
So
Huh?
z to the power
Oh, sorry. Yeah,
3.
correct. This power is wrong here. It's 3 by 2 here. This is what you were saying, beta? The power is 3 by
Sir.
2? Yeah.
So
Yeah.
z.
Yeah.
So,
Okay. Yes.
sir, in short, we can say that we are using chain rule.
Yeah. It's actually like the equivalent of chain rule for integration. That's why I said, that integration by substitution is like the equivalent method in integration for what is called the chain rule method in differentiation.
Okay, sir,
Only
got it.
it's not called the chain rule here because that chain rule is actually what step? That dy by dx is dy by dz into dz by dx. So we're not really using that chain thing. We are using substitution. Okay, so just go through all the steps in this and understand this. Okay, including the last one where we have actually proved that this is the correct antiderivative. Okay, so this proof over here, the application of chain rule for the differentiation is quite complicated. I've just written it in a single step, but make sure you understand it. Okay. This term will be 0 here. So once we understand this over here, we will do a generalization of this. Okay, so hope this is clear, people. Okay, so now let's write a sort of a generalization of this concept. Okay, we have done this with an example. Now, if we generalize this, general method, so we want to integrate a function which is of a linear term. Okay, so ax plus b is a linear term in x, such that we know that if we just had fx, its integration is ix. Okay. So what we do here is we substitute ax plus b as z. So therefore, dz by dx becomes a. So dx can be substituted as dz by a. So this integration, instead of a function of a linear term, it becomes a function of z, but then dx has to be replaced with dz by a. So it becomes 1 by a times integration of fz dz. Okay. Now, since we know that integration of fx is ix, okay, so we'll substitute this here. So integration of fz with respect to z will become iz, but there's a 1 by a term outside plus c. So on doing the resubstitution, we can see that finally this becomes like a formula that integration of f of ax plus b becomes I of z, and z was nothing but ax plus b divided by a plus c. So this becomes like a direct formula we can use. So as a very simple example of this, if I have integration of e raised power 2x plus 3. Okay. Now I know that integration of e raised power x is equal to e raised power x1. So this will become integration of, so it will become this term, but x is replaced with 2x plus 3. And of course, the antiderivative has to be divided by e, which is the coefficient. So this is 2 plus. Okay. Or for example, if I have integration of, let's say, 1 upon 3x plus 5 dx. Okay. So now for this one, I know that integration of 1 by x is ln x. Okay. So integration of this term will become ln of that linear term 3x plus 5, but that has to be divided by e, which is the coefficient of x plus c. And you can very easily check that these two are the correct antiderivatives, because if you differentiate these, you will get these functions. So this is like a direct formula that we can use once we are aware of this process. Okay, so hope this is clear. Just make a note of this, and particularly make sure you understand the two examples I've given. Then we'll do some more. And just go through your doubts. Yeah, so Darsh, to answer your question, indefinite integration is the same thing as finding the antiderivative. Just like differentiation is the same thing as finding the derivative. And Manav, to answer your question, no, integration part for the upcoming major test will be only up to what we have done in the last lecture. Today's lecture part will not be asked in the upcoming test. Okay, so only up to what is there in worksheet 6. So that is simple application of x to the power n type of integrations with the properties. So trigonometric functions, then simple substitution that we are doing today, all this thing will not be asked, and application of integration will not be asked in the upcoming test. That will be there in the next test after that. So it's clear to both of you, Manav and Darsh, both the points. Right?
Sir, then does the integral have a different meaning than the antiderivative, or does
Sorry,
it differ?
Darsh, a little bit louder, please.
When we say the integral of a certain thing, then it means the same as the antiderivative.
Antiderivative. Yeah. So see, integration is the process. Okay. And what is the result of the process? It gives us the antiderivative. Got it, no?
Okay, sir. And this is
Like differentiation is an operation, no? But on differentiating or on applying differentiation operation, what it gives us? It gives us the derivative. So like that, on applying the integration process or operation on some function, what it gives us? It gives us the antiderivative.
okay, sir. And this is just for indefinite integration.
Correct. Like the proper name of that term is indefinite integration.
Okay, sir.
There is also another type of integration which we'll discuss, which is called definite integration.
Okay, sir. Sir, so when in the formula here you have written I of ax plus b, in the same place can we use like the integration symbol instead of I? Or does that have a different meaning?
Okay, so let's do some examples. Okay, so just work these out quickly. They're quite easy, as you can see. So they're more or less application of the same formula. Okay, very good, Vinny. That's correct. Just a moment, I'll share the file again. Just a moment, people. My file has crashed. I'll just restart it. Share it again. Right. So very good. So you're all getting the correct answers mostly. I'll just verify the answer again for you. So integration cos 2x will become sin 2x whole divided by 2 plus c. Because we know that integration of cos x is sin x. Okay. So therefore, integration of cos of any linear term will become sine of that same linear term, but divided by the coefficient of x plus. That's what we are applying over here. Similarly, the second one, dx upon square root of 3x plus 2. That will become 2 times square root of 3x plus 2 divided by 3 plus, because we know that integration of dx by root x is 2 root x plus c. So integration of dx upon square root of any linear term will become 2 times that linear term's square root divided by the coefficient of x plus. So just using the application of that same little formula everywhere. So we don't even need to do the steps of substitution. We can directly do this. Of course, we can do a question like this by substitution also. Okay. So we can go the lengthy way. We can substitute first 3x plus 2 as z. So dz by dx, that becomes 3. So that means dx becomes dz by 3. So this integration this will become 1 by 3 dz by root z. So that we know will become that's how we'll finally get 2 by 3 into square root of 3x plus 2 plus c. But all these steps are not required because we can directly come from this step to this step because we have now reduced it to a general formula. If we reduced it to a general formula that integration of a linear terms applied to a function is the indefinite integration of that function on that linear term divided by e plus c. So by using this, we can directly circumvent all this. Okay, so let's work out the other two. So we had this and this. So let's start with this one. So integration of dx upon 5x plus 1 to the power 2 will become minus 1 upon 5 into 5x plus 1 to the power 1 plus, because we know that integration of dx by x square is minus 1 by x plus c. Again, we are applying that concept. And this is probably the simplest one of the lot. It's the same as the one we had discussed earlier. Okay, so hope all of you are clear with this. Remember, this integral basically it is integral of x to the power minus 2. So that is x to the power minus 2 plus 1 upon minus 2 plus 1 plus c. That's how it comes out to be minus 1 by x plus. Just be a little bit alert when the powers are negative quantities, like in this case. Okay. It's easy to make a mistake that it should be x cubed by 3, but for that the x square should have been in the numerator. Here the x square is in the denominator, so it's anyhow. So that completes this type of substitution. Now we will come to more examples of substitution also. Okay, but before that, we will take a look into the second type of operation in integration, which is called definite integration. Okay, so this is sometimes also called integration with limits. So what definite integration does is, this is an operation that calculates the area subtended by the graph of a function between any two what we call limits. So the symbol for the operation is like this. It's an integration symbol with the function, but in addition there are two values which are written above and below like this, or it can also be just written like just the values. Okay. So for example, it could be integration of sin x with respect to x from x equal to 0 to x equal to pi, let's say. So now how this symbol is read, okay, or how it is interpreted, is that it is the definite integration, or this for that matter. This is read as definite integration of the function fx with respect to x, okay, from lower limit x equal to a to upper limit x equal to b. So these things here, they are called the limits. This is the lower limit. This is the upper limit. Okay. Now, so far we've just understood the symbol and what it represents, roughly speaking. Okay. We will discuss about how we calculate this also. So this one is, for example, definite integration of sin x from x equal to 0 to x equal to pi.
So, sir, can we say that the value written above the integration sign is basically the domain?
It's actually like a codomain. It has to be has to be like part of the domain.
So, sir, earlier when
So
we
for
were
example,
doing,
sin x function's natural domain is what? -2 plus infinity, na? But here I'm integrating only from 0 to pi. So always the limits have to be, some subsection of the domain. It can be the entire domain also, but it can be some sub-interval of the domain also. You following, Navita?
yes, sir. So, in can we say that in indefinite integration, the domain was minus infinity to infinity?
No. But see, indefinite integration is a different thing. It has nothing to do with area. So when I
Okay.
explain how this calculates area, indefinite integration's only purpose is to give you a function which is anti-derivative. Got it, no?
Okay, sir.
Whereas this one's purpose is different. This one's purpose is to actually calculate the area under the curve of fx from the limit x equal to a to x equal to b. So we'll come to the interpretation next. Okay. First, let's just get comfortable with the symbol used over here. So you can think of this like a different operation. The purpose of this operation is different. Is to calculate area under the curve. Whereas the purpose of the indefinite integration operation was to give us the antiderivative.
Okay, sir.
So what this does is that if the graph of the function fx is this, so if we plot y equal to fx, suppose that graph is this. Suppose some arbitrary function I've taken which has some arbitrary domain is represented by this graph, but the point x equal to a is over here and the point x equal to b is over here, suppose. So then this area subtended by the graph of the function, okay, between the two vertical lines x equal to a and x equal to b. So this area is actually calculated by doing this operation. So this definite integration operation, it gives us, its value is the area under fx between x equal to a to x equal to b, this area. Okay. So for example, for this one, the interpretation would be like this, that we know that the sin x graph is something like this. It's like this continuous wave shape kind of thing. Okay. But this is the point pi. This is the point 0. So this area would be calculated by this value. Okay, so it's the area subtended by the sin x graph on the x-axis between the points x equal to 0 to x equal to pi. This would give us that. This would give us the area under the sin x graph between x equal to 0 to x equal to pi. Okay, so now let us see how we actually calculate this. So how do we get the value of this integration? So it turns out that the value is calculated using the antiderivative. That is where the indefinite integration becomes important of fx. So basically, if the antiderivative of this function is ix, okay, then the value of this becomes the value of the indefinite integration at d minus the value of antiderivative at t. So let's understand this with a quick example. Okay. So for example, integration of x square, if I want to do from x equal to 0 to 1. So I know that the indefinite integration of x square is x cubed by 3 plus c. So this will become the value of this function. This is my ix, okay, because this was my fx. Okay. It will become the value of this function at the point 1 minus the value of the antiderivative at the point 0. So at the point 1, what is the value of the antiderivative? It is 1 by 3 plus c. At the point 0, it is how much? 0 plus c. So c always cancels out and we get 1 by 3. So as it turns out that 0 to 1 integration of x squared dx will be given by 1 by 3. Okay. Similarly, just to see what we got there, sin x from 0 to pi would be how much? Now we know that integration of sin x, the indefinite integration, gives us antiderivative of minus cos x plus. So this would be minus cos pi minus of minus cos 0. C will anyway cancel out. So minus times minus 1 minus of minus 1. So interestingly, it gives us the value of 2. So this integral is equal to 2. So what this means is that that area is of 2 units. This area, this is integration sin x from 0 to pi. As it turns out, it's 2. Okay. This means that if you consider the graph of x square, the graph of y is equal to x square is something like this. So if I take 0 to 1, then this area would be equal to 1 by 3. And right now we will not worry about the unit of the area, okay, because we're just treating x and y like numbers. Okay. Later we'll see that when they're physical quantities, then the area also has some physical unit. Okay, so I'm just going to scroll up a bit so that you can write down the whole thing or go through it at least. Then you can come to the 2 examples below. Okay, so let's just do a couple of examples and wind this up. Okay, so now let's do an example to illustrate this point a little bit further. So we want to find out, let's say, integration of x dx from, let's say, 1 to 5. Okay, so find this out, and then what we want to do is show that the value of the above definite integral gives the area, okay, accurately as verified using geometry. So what the question is saying, that in this particular case, we should be able to verify the above result geometrically also. So just try this out and it will bring clarity to that whole point of how it calculates the area under the curve. Okay. So first calculate this thing by the method of integration that we've learned. Okay, that, and then you can show that if you also calculate the area geometrically, it verifies what we are getting from the definite integral value. So use this general formula for this, okay, where Ix is the antiderivative of fx. Yeah, very good. So you'll get the value as 12. So let's first do the integration. So we know the integration of x is x square by 2. Okay. So this will become this is 12. Okay. Now you can also verify that this actually gives you the area, because in this case the function that we're talking about is a simple linear function. So this integration that we are doing from a to b, so the function is x. So y is equal to x. This is what we have to plot now. That's a simple straight line which has a slope of 1. So this is our function y is equal to x, and let's say this is the value 1, and somewhere here is the value 5. The area we are talking about is this. So this area will be this way. Now this area is area of a trapezium. So it is half into sum of parallel sides into distance between them, which is 4. That's 24 by 2. So that's 12. So it verifies that this area is correct. So in a way, this kind of justifies how definite integration gives us the area under a curve, albeit we have proved it for a linear function. But the theory of calculus is that any curve can be broken into a set of small little linear curves or linear terms from point to point. So anyhow, so with that we complete today's session. So thanks for attending, and that's it for today. Wish you all the best for the upcoming test. Just make sure that you do the revision of worksheets 4, 5, and 6 very carefully. Worksheet 6, I'll be sending you the detailed solutions in another couple of days. So by then, please complete it and verify the solutions. Okay. Yeah, I'll. So that's it for today's session, people. Thanks a lot for attending.
Thank you,
Thank you,
sir.
sir. Bye, sir.
Thank you, sir. Bye, sir.
Okay, bye.
Thank you, sir. Bye.